In this last section, in this lesson, we're going to talk about the concept of impedance. So here we have an RLC circuit. So it has a resistor, it has an inductor, and a capacitor, all in series with an AC power source. So in AC circuits, resistors resist the flow of electricity, right? Resist the flow of current. That's the point of a resistor. But in AC circuits, inductors and capacitors also have, the reactance, the capacitive reactance, the inductive reactance, that also resist the flow of electricity. So when you put all these things together, you expect, well, they should impede the flow of electricity even more. But you can't simply add their effects. You can't just linearly add up their capacitive reactance, inductive reactance, and resistor values to figure out how much does an RLC circuit resist the flow of electricity. Because inductors and capacitors act in opposite ways. Remember, inductors prevent high-frequency signals from getting through. If you have a low-frequency alternating current, the current more easily passes in an inductor. And for a capacitor, the opposite is true. High-frequency current passes more easily through a capacitor. So when we combine these, there is a way to combine them. You just can't simply add them together. The collective effect of these three devices on the flow of electricity in this circuit is called impedance. Now, impedance, of course, is a synonym to resistance. You could resist something or impede its motion. Impedance, we use a capital Z to represent impedance. And of course, impedance has units of ohms, just like reactance does, just like resistance does. The impedance is equal to the square root of the resistance squared plus the difference in the reactances squared. Now here I have the inductive reactance first minus the capacitive reactance. But hopefully you can see it doesn't matter what the order is because you're going to square the difference. So if x sub L is greater than x sub C, this is a positive number and we'll square it. If x sub C is greater than x sub L, this becomes a negative number, but we still square it. So it ends up being positive. So if these two values are different from one another, if they aren't the same, it leads to a positive contribution to the impedance. It doesn't matter if the reactance is more than the inductive reactance is more than the capacitive reactance, or if the capacitive reactance is larger than the inductive reactance. If these two things are different, the impedance goes up. And of course, the impedance is proportional to the resistance as well. If the resistance goes up, the impedance goes up. So how do we figure out the amount of current that goes through this circuit? Well, the equation is fairly straightforward, like it was before the other three examples. The current is equal to the voltage over the impedance in this RLC circuit. So we need to know what the impedance is in order to get the current. Hopefully you can see that as the impedance goes up, the current goes down, right? If you impede the current more, you get less current. How do we minimize the impedance? Well, there's nothing we really can do. We can minimize the resistance value, which minimizes the impedance. Hopefully that makes sense. Put a smaller resistor in here. You have a smaller resistance to the flow of electricity, therefore the impedance is smaller. But these two things together, in order to minimize this term, we want them to be equal to one another, right? If these things are equal, this minus this is 0, so it doesn't contribute at all to the impedance. When the inductive reactance and capacitive reactance are equal to one another, the current in an RLC circuit is maximized, and we call this resonance. Now, how do we set these equal to one another? Well, we could, of course, change the capacitance value to something or change the inductor out to something else. But the easiest way to change the inductive reactance and the capacitive reactance is by changing the frequency of the oscillation here, right? Because both reactances depend on frequency. So we can calculate at what frequency do we need to oscillate in order to make the current going through the circuit a maximum. So we set those equal to each other. Remember that x sub L is 2 pi times the frequency times the inductance. X sub C is 1 over 2 pi times the frequency times the capacitance. So we set them equal to each other. F naught here becomes the resonant frequency. Rearranging this equation, you should have the algebra chops to do that. Multiply both sides by F naught, divide both sides by 2 pi L to bring it over, take the square root, and you end up with this frequency that causes the reactances to be equal to one another is equal to 1 over 2 pi times the square root of the inductance times the capacitance. This is called the resonant frequency. Well, why do we care? Well, you actually use this all the time. If you have a car radio that you tune, nowadays it's all digital, so you don't really see what's going on, but if you have an old school radio or an old school car stereo, if you have a classic car with the old style dial tuning for the radio, what you're doing effectively is changing the capacitance of your circuit. So all around us in the air, there are broadcast signals, right? From here in Wausau, 90.9 FM, which is WPR, Wisconsin Public Radio, to 105.7, which is a rock station in town. You have dozens of different radio stations at those specific frequencies, right? 90.9 FM is 90.9 megahertz. It's a frequency. 105.7 FM is 105.7 megahertz. And the AM frequencies, those are kilohertz. So you have 700 kilohertz or something like that. So in order for your car stereo to amplify the signal at a specific frequency, we want that frequency to create a resonance in the car stereo. We want the other frequencies to be ignored, to not change things in our car radio. We want to amplify the signal that we desire. So to do that, old car radios would have a dial that you would spin, which would actually change the capacitance in the car radio. If you change the capacitance, you change the resonant frequency. So effectively what you're doing is you're tuning your circuit to be sensitive to a very specific frequency of radiation, of oscillation. And that's the oscillation that's amplified in your car radio. And if you don't want that station amplified, you turn the dial, turn the capacitor to a different station. Now this is still done in your car radio, but it's not as obvious as it was in the older ones, where you actually had to tune in with a capacitor. So this is the idea of resonance. And that F naught there is called the resonant frequency. At that frequency of oscillation, you get maximum current through the circuit. If your frequency is lower than that or higher than that, you get less current through. Because if your frequency is higher than that, the inductive reactance becomes stronger than the capacitive reactance, and this term is no longer zero and contributes to the impedance. If it's lower than that, if your frequency is smaller than that, X sub C becomes greater than X sub L. You think, well, that becomes negative, right? No, we're squaring it, so it's still a positive term and contributes to the impedance. So at resonance, you get maximum current flow through this circuit. In an inductive reactance circuit, we talked about how the voltage led the current. In a capacitive reactance circuit, we talked about how the voltage lagged the current. In a resistive circuit, we talked about how the voltage and the current were in phase. So what happens when we combine all three in an RLC circuit? Well, typically the current and the voltage are not in phase in an RLC circuit, with a notable exception at resonance. At resonance, at the resonant frequency, you can calculate what that frequency is, you get the maximum current out, and the voltage and the current are in phase with one another, which means that when the voltage peaks, the current peaks. When the voltage is zero, the current is zero, and so on. This only occurs at resonance. If you're not at resonance, you can still calculate what that phase difference is. Remember, a phase difference, think of it as an angle, like a rotation, and not like a moon going around a planet. When it makes one full revolution, 360 degrees or 2 pi radians, that's one complete phase, one complete cycle. If you're off by a quarter of a phase, a quarter of a cycle, then you're at 90 degrees or pi over 2. If you're half a cycle off, then the angle is pi or 180 degrees. this is the equation to calculate what that phase angle is. So, if you know what the resistance value is, and you know what the impedance value is, which depends upon resistance and the two reactances, then you can calculate what the phase angle is of the circuit. At resonance, the impedance is equal to the resistance. So this is equal to 1 cosine of 0 is equal to 1. So the phase angle would be 0, which means that the current and the voltage are in phase. If you get some other angle up, that means that the current is leading or lagging the voltage. Now, that tells you the phase angle. That's important when talking about how much power is dissipated by the circuit. The average power in an RLC circuit is given by the following equation. The average power is just the RMS current times the RMS voltage. And if I stop there, that would be basically the power emitted by just a simple resistive circuit. P equals I times V. We talked about that when we talked about simple circuits with resistors in them. But for an RLC oscillating circuit, there's an additional term here called the power factor. That is this cosine of phi. So this is the power factor. It's between 0 and 1, so cosine of phi will be between 0 and 1. At 1, at resonance, you get the maximum power out. When cosine of phi is 0, no power is strongly dissipated by the resistor. And if you think about it, that only occurs, if you look at this cosine term, when resistance is 0. When the resistance is 0, what cosine of theta is equal to 0, no power is dissipated because there's no resistor. You just basically have an inductor and a capacitor that will have the circuit oscillate forever. If you include a resistor in an RLC circuit, you have to have an external power supply constantly regenerating the power, because whenever current flows through a resistor, that resistor heats up and gives off energy. So this power is dissipated by the resistor alone. When in an ideal inductor, when current goes through, it resists the flow of current, but it doesn't radiate that power away like a resistor does. And a capacitor again can resist the flow of current depending on how rapidly that current is oscillating, but it doesn't radiate away the energy, it just pushes back. Whereas a resistor takes some of that energy and basically throws it away as heat. Because a resistor dissipates the circuit, you can dampen the oscillations with an RLC circuit. Just like, for example, if you have a spring attached to a block of some mass, and that mass is on a table. So if I push or pull this spring, I can get this mass to oscillate back and forth. If there is no friction in the system, no air resistance in the system, this thing will oscillate forever. If there is no power being lost in an RLC circuit, the current will go back and forth, back and forth, back and forth forever. And there's an app I'll link to that allows you to see this. Adding a resistor in an RLC circuit is very much like adding friction to this oscillating system. So every time the block moves against the table, kinetic energy is lost into heat, thermal energy, and then this block will eventually slow down and come to rest. In an RLC circuit that's not getting additional power from outside, where it's just the current oscillating itself, eventually that current will die off as all of that power will be radiated out by the resistor.